Now I'd like for you to determine whether the sum as n goes from 1 to infinity of 6 to the n over 5 to the n minus 1 converges or diverges. Pause the video and come back when you have an answer. Kind of ignoring the 1 gives us an idea of a comparison series. I'll compare 6 to the n over 5 to the n minus 1 to 6 to the n over 5 to the n. Because again, as n approaches infinity, the minus 1 becomes really unimportant. 6 to the n over 5 to the n can be written as 6/5 to the n, and because 5 to the n minus 1 is a smaller denominator, I know we have a larger overall result. As it turns out, we have now a series that is larger than a divergent series, and we know that the sum as n goes from 1 to infinity of 6/5 to the n diverges because it's a geometric series with the absolute value of r, the ratio, greater than 1. Therefore, our original series, the sum as n goes from 1 to infinity of 6 to the n over 5 to the n minus 1, diverges by the comparison test. I think you could get away without writing this equals 6/5 to the n. Other than that, everything else I've written here would be required for full credit. Let's look at another one. It is the sum as k goes from 1 to infinity of k times the sine squared of k divided by 1 plus k cubed. This one's a little trickier, but I again want you to pause the video and see if you can make some progress with it and come back when you're either done or stuck. The sine squared of k in the numerator might throw some people off, but I made a note here that sine squared of k is always less than or equal to 1. Therefore, k times the sine squared of k over 1 plus k cubed is less than or equal to k over 1 plus k cubed. Now I want to compare that. Again, we're going to kind of neglect the 1 here, and I'm going to compare k over 1 plus k cubed with k over k cubed. Since 1 plus k cubed is a larger denominator, we have a smaller overall result, and therefore we have that k over 1 plus k cubed is less than or equal to k over k cubed, which then reduces to 1 over k squared. We know that 1 over k squared is going to converge, so I'm going to go ahead and write, or I already went ahead and wrote the answer as the sum as k goes from 1 to infinity of k times the sine squared of k over 1 plus k cubed converges by comparison with the sum as n goes from 1 to infinity of 1 over k squared, which converges because it's a p series with p greater than 1. The key in this case is this long strung out inequality that we have. We have the given series on the left is less than a convergent series on the right. You may say, but you didn't say what test you used. Yes, I did. By comparison with, and right there I implied what test I was using. And here we have the final answer. That wasn't right. Here we have the final answer. Gosh, have to include the original series, right? One more. I again want you to give this one a shot. We have the sum as n goes from 1 to infinity of 2 over the square root of n plus 2. Pause the video, come back when you're done. My first thought is that I want to compare, so I'm looking at 2 over the square root of n plus 2, and I want to compare that to 2 over the square root of n. I notice that the denominator on the left, square root of n plus 2, is larger, so I have a smaller overall result, but 2 over the square root of n is divergent, we know that. So I have the wrong inequality relationship. That means I cannot use the comparison test. I still want to use something related to 1 over the square root of n, and so I'm using the limit comparison test with the sum as n goes from 1 to infinity of 1 over the square root of n. You can use 2 over the square root of n too, doesn't matter. And if you did, you found you had a different limit, but it's still positive and finite, isn't it? Here I have the limit as n approaches infinity of 2 over the square root of n plus 2, all divided by 1 over the square root of n. So I flip out the denominator and multiply, and we end up with the limit as n approaches infinity of 2 times the square root of n over the square root of n plus 2. Dividing out the largest power of n that appears in the denominator means I'm going to multiply numerator and denominator by 1 over the square root of n. That leads us to the limit as n approaches infinity of 2 over 1 plus 2 over the square root of n. And as the square root of n is in a denominator, as n goes to infinity, that term goes to 0. We end up with 2 as a result. Again, positive and finite. So we wrap this up by saying, since the sum as n goes from 1 to infinity of 1 over the square root of n diverges, now we got to say why. It's a p series with p less than or equal to 1. The series diverges. And that's going to be good enough for the final answer. And you say, but you didn't say what test you were using. Yes, I did. I said use the limit comparison test way up here. A slightly different way to format the answer, but it works just the same. One final note. If we use the comparison test, we can estimate the sum of the infinite series, S, by finding a partial sum, S sub n. There will, of course, be error involved. If our comparison series is a geometric series, then the remainder sub n is less than or equal to the sum of the remaining terms, as I goes from n plus 1 to infinity of a sub n. We would find that sum using the formula for an infinite geometric series, and the remainder is less than that sum because if we use the comparison test, sigma a sub n is less than or equal to sigma b sub n. In this case, the geometric series would be the b sub n series. If we used a p series, then remainder sub n is less than or equal to the integral from n to infinity of f of x dx, the related function, like we saw with the integral test. And again, the inequality holds because of how the comparison test works.